What's up, everybody? It's Dan from SageMathTutoring.com, and here we are with another video. This is for an AP Physics class, and it looks like we have some problems we need to address here. So let's see. A satellite orbits a planet of mass m and radius r. The height of the satellite above the planet's surface is 3r. Okay, this is a beautiful diagram. Totally approve of this diagram. Look at this. You got the radius from the center all the way to the surface. We know that the distance between the surface and the satellite, by the way, this should be the center of the satellite, you know, a little center right there. That distance is 3r. So already my student doing a great job making a picture. Okay, the ratio of the gravitational field on the planet's surface to that at the location of the satellite is. Okay, so looks like she said 9. The equation, the formula that you're going to want to use is definitely this one. This is gravitational field. We're going to call it F. Okay, and let's just be clear. Gravitational field. Okay. Not to be confused with like just force per se. Okay, so that's the gravitational field, and that's going to equal the constant of gravity times the one mass times the second mass, and then the distance between the two objects squared. Okay, now this gravitational constant is an interesting number. It's one of the constants that is sort of embedded in nature in the same way that pi might show up, in the same way that E might show up. This G right here is about 6.673 times 10 to the negative 11. All right. Now, the good news is you actually don't need to know that for this problem. This problem is only concerned with the ratio of the gravitational field on the planet's surface to that at the bottom at the location of the satellite. So really we're just looking for this ratio, F, you know, the F as it pertains to the surface of the planet over, surface, over the F as it pertains to the location of the satellite. Okay. That's the big picture. I'm a huge fan of tackling these problems, looking at the big picture first. So at the end of the day, well, let's flesh this out, you know, using this thing. It's going to be the gravitational constant times the mass of one of the objects. Now the mass of one of the objects is this big M, right? A big M times the mass of this little guy. Now they didn't tell us what that mass is, so we're just kind of stuck with maybe calling it little m. Okay, little m, and maybe I'll call this m1, m2. So, you know, when we're fleshing this out, we need to realize that we're really dealing only with the gravitational force at the surface, and therefore the distance that we're considering when we're considering the gravitational force at the surface, that's this point. When we're considering the distance, well, we're considering the distance between the blue point and the green point. That's important insight for this problem, that when it comes to the gravitational force at the surface of this planet, the so-called distance between the objects would be the distance between the surface and the center. So if you don't catch that insight, then this one's going to be super confusing. So that's going to be all over the radius. It's just one radius, right? And then it's radius squared. Okay. Now, this big R stands for the radius of the Earth. This little r stands for the distance between the two objects you're analyzing. Okay, so that's important that you realize. You want to not associate this little r necessarily with a radius. Okay. This little r stands for the distance between the two objects you're analyzing. This big R is literally the radius of the Earth, which, by the way, happens to be the distance between the two, we could say, locations that you're analyzing. All right. So we have just figured out a nice expression for the gravitational force at the surface of the Earth. So we're going to put all of that over another expression that has to do with the gravitational force at the location of the satellite, when it comes to, as it relates, we could say, to the center, this green center, okay? So we related the blue dot to the green center. Now we're about to relate, we could say, the yellow dot. I'm going to make that yellow to the green center. So now we're going to have our G. Still, the masses are the same. Nothing's changed about that, right? But now the distance is different, right? Instead of r squared, well, think about it. It's not 3r because we want to know what's the distance between the center of this satellite to the green dot. That's what we need. The distance between these two objects is the distance between the center of the two objects. And the distance between the green dot and the yellow dot is 4r. Can you see that? That's important that you see that. So therefore, underneath here, it's going to be 4r squared. So we are really close to finding the ratio of those two gravitational forces. That's what we're going to do right now. Well, bottom line is you have a fraction divided by another fraction. That's the reality of it. So what do you do when you have a fraction divided by another fraction? Well, you keep the first fraction, right? We'll keep it color-coded. Keep the first fraction. And then you, of course, multiply that times the reciprocal of the second fraction, which is 4r squared all over g times m1, m2. Okay? Look at all these cancellations. The g's cancel. The m's cancel. Thank God, right? But now we have to be careful with this part. When we square this quantity, this product, that exponent of 2 gets applied to both of those. So therefore, we end up with, looks like it's 16r squared up top, right? 16r squared up top, and down below, this guy is still here, right? So that's going to be r squared, and then we can cancel the r squareds, and we are left with 16. That is the answer to that one as far as I could tell. Pretty sure. It's that one. All right, looking at this other thing. Satellite of mass m orbits a planet of mass big M and radius r. The height of the satellite above the planet's surface, 3r. Force exerted on the satellite by the planet is F. Force exerted on the planet. My view with this problem is that the force is going to be the same. So my thought is that this one, because even if we were to rely on this formula here, let's say we acknowledge, oh, okay, let's take into account the first thing they said. The force exerted on the satellite by the planet is F. Okay, so we're going to talk about that. F is the force exerted on the satellite by the planet, and that's going to be, this, G, and then it's times big M. I'll call it M sub 1. We're going to call this little m, okay? Actually, we'll just call it what they told us to call it. It's going to be big M and little m, all right, because they literally told us to call it that. So we have big M, little m, and then it's going to be all over the distance between them. And the distance between them is most definitely 4r squared. Now, That is the blue statement. A force exerted on the satellite by the planet is F. Well, we just represented that. But then they're like, the force exerted on the planet by the satellite in terms of F is what? Well, that's the green situation, which we're going to bring over here. Well, wouldn't that be question mark equals, well, certainly the gravitational constant, big M times little m, right? Because we're entering the same information. And then you have to put the distance between the satellite and the Earth. Well, that's going to be the same thing, right? Isn't it just going to be the same stuff? So I don't see why it would be different. I don't think it is different. I think it's just F because apparently anytime you see this, well, it really just means F. So anytime you see this, well, it really just means F. So that should be F. Okay. So I think it's kind of like a trick question. If that makes sense. So that's something to take into account. Yeah, feeling pretty good about that. Okay, next problem. Let's see this disaster. A block of mass 0.5 kilograms, there it is connected to a 1.2 kilogram block, there it is, by a light string that passes over a massless and frictionless pulley. Okay, no friction, cool. A cup of mass 0.1 kilograms attached to the top. Okay, so this is a cup. This is their terrible drawing of a cup. Never seen a cup that looks like that, but we're going to go with it. Cup of mass 0.1 kilogram attached to the top of a 1.2 kilogram block. Okay, so the cup is attached to the top. Okay, so it's a cup tilted to the side. Maybe that's what it is. Okay, and then we have this little thing there, attached to the top of this, and there's a little ball in there. Okay, great. Yeah, literally a contraption that's wasting everybody's time. The tabletop is frictionless, the system is released, and at rest, the 1.2 kilogram block accelerates to the right and is moving 0.8 meters. Okay, 0.8, there's a stopper, so it goes whoop, and it hits the thing. Collides with the stopper near the end of the table. Ball continues to move, lands on the floor at a position 3 meters below. The ball's like, boom, 3 meters below. All right, good times. Draw free body diagrams representing the forces, not components, acting on the 0.5 kilogram and 1.2 kilogram blocks. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Okay, so this is the teacher's style with free body diagrams, so I actually kind of like this. Draw the relative lengths of all the arrows to reflect the relative magnitude of the forces. Okay, so focusing on the 1.2 kilogram block, that is right here. There's definitely the weight pressing down, that's mg. But it's total m times g. There's a bunch of masses to take into account, so let's kind of focus on this blue arrow. The blue arrow is m, well, we could say mg, but there's a bunch of masses to take into account. We have the 1.2 kilogram mass. We have the 0.1 kilogram mass. We have the 0.2 kilogram mass. So you are going to have to add all that. So that's going to be, I guess, 1.3, 1.5. Yeah. 1.5 mass, total mass, times gravity, which is 9.8, and that is 14.7. So let's get that in there, 14.7. And let's see. Well, that would be matched by an equal normal force of 14.7. Okay. 0.5 block, kilogram block, that's this. Well, there's the tension. There's the tension that is pulling up. And, oh, I forgot this tension too. So this tension is right here. And that should definitely be the same as this tension. So if we make, let's make this guy sort of 2 units long. And it looks like the student sort of did that, actually. We'll make this one 2 units long. And it kind of looks like the student did that. So we're going to make this 2 units long because we want to make sure that that tension is the same. This is mg, the weight times gravity of just the 0.5. And that would be 0.5 times 9.8, which is this. Looks like we got that. So in total agreement here, this should be larger than this arrow because it is actually moving down. The only situation where the tension arrow would be the same as this weight arrow would be if the block was in equilibrium and kind of stuck there, right? But we're analyzing a scenario where the block is actually moving down because it's released. Let's see, looking at over here, calculate the acceleration of the 0.5 kilogram block. Well, there's always the formula, force equals mass times acceleration. Now, I think, at the end of the day, the force that is moving this down is the weight. Now, I understand what my student is doing here with the minus t, like that makes sense to me. Something seems to be going awry over here, but I think probably to approach this in a little bit more of a simple way, it would be better where, let's just say, okay, we have the force, pulling this down, but the mass should be the total mass of everything. We have the mass of this and all of that as well. Okay. I think that's probably easier to do to find this acceleration here. So the force really is equal to the mass of the entire system times acceleration. And by the way, that's always the case. Even if it's a simple, single block, force is always going to be the mass of the entire system times acceleration. So I think that should work. Now, again, we're focusing on the acceleration of this guy, right? Now, the acceleration of this is going to be the acceleration of all of it, isn't it? So what we're looking for is when we say, what's the acceleration of this? We're really saying, what's the acceleration of the entire thing? So you could just kind of treat this as one single unit, and the force that's being exerted is clearly the 4.9 that we already found. It's that weight going down, okay? That's the way I would go with it. So we'll bring that over here. We're looking at 4.9 equals the mass of the entire system times the acceleration. Now, what is the mass of the entire system? Well, that's what you get when you add this mass plus the cup mass plus this mass. And when I add all of these masses up, I actually get literally 2. So if we want to find out what the acceleration is, it's going to be A equals 4.9 divided by 2. And A therefore equals 2.45. So that should work for that one. We'll get a little divider action here. All right, looking over here, calculate the speed of the ball right when the block hits the stopper. Okay, that's good. That's going to be the final velocity. That's the original velocity. 2 times the acceleration times the distance. I love that. That's great. The original velocity is 0, so it looks like my student's ignoring that. Ignoring it in a good way, right? We don't have to write 0 on the next line. We're looking at 2 times the acceleration, but the acceleration is 2.45 times the distance. So I think that's what we need to do. So I'm going to rewrite it. So we have v squared, vf final velocity squared, times 2 times the acceleration, which is 2.45, I believe, times the distance traveled, which is 0.8 meters. And that is found right here, right? That's how much distance it travels. Right before it hits the stopper, right? So this over here is gonna turn out to be 3.92, but of course, we'd have to take the square root of that. So we're looking at the final velocity is equal to 1.979. So it's almost like 2. All right. I'll call that 1.98. And that should be meters per second. So cool. All right. I feel pretty good about that. Okay, so then we would bring in this other scenario. Calculate the horizontal distance traveled by the ball after it's released from the cup, the horizontal distance. Well, to be honest, I really like where my student's going with it, because my student's kind of emphasizing the fact that, well, the distance traveled is going to be the velocity, in that x direction, times the amount of time, right? I mean, that's what's happening. This thing goes here, and then the ping pong ball flies off, and it travels a horizontal distance for a certain amount of time. I mean, that's what it is. But the problem is we have to find out, well, how much time actually elapsed, because we do have the velocity. We just found the velocity in the last problem, right? The velocity of this ping pong ball, once this thing hits the stopper, that velocity, we can say the original velocity, at the beginning of the observation, is 1.98, right? We've got that here. So assuming we did this correctly, I don't think I made a careless mistake, but assuming there were no careless mistakes, that's actually the final velocity of the ball when it hits the stopper is the original velocity of the ball as it flies in that direction for this analysis. So I am with my student 100%. So it just looks like it should be 1.98 right there. So this right here should be 1.98. And we haven't really even talked about this formula. So what my student's doing, which is really good, is acknowledging, oh, okay, well, in order to find out the t, well, really what we have to do is we have to find out how long does it take for the ball to go down. We need to consider that y component, because this ball, how long is it traveling to the right? Well, the question is, how long does it take to go down and hit the floor? Because once it hits the floor, well, guess what? It's not traveling to the right anymore. So we need to find out how much time does it take for it to travel 3 meters down. That's ultimately what we're doing, right? So my student did a great job here. -3, that is we're going down. The original velocity is 1.98 times t minus, it's really 1/2 g, right? For a free fall situation, it's minus gt squared, right? So all this is actually really good. It looks like the only issue is that right there. So if I was to plug into all this, it'd be like 1.98. I'll just call it minus 4.9. That should be a t, my bad. Whoops. Minus 4.9 t squared. And then, yeah, going through the motions, the sort of annoying motions. I'm going to set the whole thing equal to 0, actually. T plus or minus 1.98 t minus 3 equals 0. So the t could be found, I guess, with the quadratic formula. So t would equal, after applying the quadratic formula, t would equal, and assuming I put in my calculator correct, I mean, we're looking at negative 1.98, which is really just positive 1.98. It's really going to be plus the square root of negative 1.98 squared minus 4 times 4.9 times negative 3 up top, and then that's going to be all over 2 times 4.9. So when I did that on my calculator, that ends up being 1.01, and that would be seconds. So then we could just plug that in, to this one. And we could say, okay, well, how much horizontal distance does it travel? That is going to be the original velocity at the start of the observation. Now, once again, once you hit the stopper, that's the beginning of the observation. So once it hits the stopper, we're looking at a velocity of 1.98, right? 1.98 times the time, which is 1.01 seconds. And that happens to be 1.9998, which is really just approximately 2. And 2 what? Well, meters. That's what it would be. So once again, unless I make careless mistakes, feel pretty good about this. For my student at home, when you're sort of redoing these problems, just check your own calculations. I don't have an answer key to refer to, but the process itself, as per usual, is sound. So just kind of check it with your own calculations if you could. Use the calculator, for example, the quadratic formula. Let's get a little divider here. This is the section where it's the final answer. This is the equation, basically the same equation up here, only with, instead of 2.23, we put 1.98. Okay. This looks like it's correct, which is the happy face, so I don't care about that one. Okay, 2 blocks of masses 3m and m are connected by a light string that passes over a massless and frictionless pulley. The mass of the block of mass m, which is here, is on a rough plane that makes an angle theta with the horizontal. The coefficient of static and kinetic friction, okay, are those. The block of mass m is held in place by a string 2 and is attached to a fixed stopper as shown in the figure below. The entire system is initially at rest. Your answers to the following questions can only be given in terms of given quantities and fundamental constants. Calculate the tension in the string 2 such that the system is at rest, assuming that it's at its breaking point. Well, I can see what my student did here, which is really good. My student calculated the force associated with maximum static friction, which is definitely this. That's the normal force times the coefficient of static friction. And then what my student did is she set that force equal to the counterbalancing forces. You have the kinetic friction here that's pushing the block in that direction. You have the tension of the string pushing the block in that direction. And you also have the component of this vector here, mg sine theta, which is the force that would sort of slide this just down, partly due to gravity, right? You're sliding it down. So what my student is acknowledging is that once you kind of break past the breaking point of static friction, well, the force associated with that moment in time is this, but the string is still holding it in place. So there's this equilibrium going on, which makes this force, which would make it necessary that this force is countered perfectly by these other forces. And then what my student did is she solved for T2. Now I get all that. I don't know exactly. The question marks are very vague. Um, you know, I'm going to throw this out there. Now, I could be completely wrong. My student would know. My student knows her teacher better than me. But, if it's at the breaking point, I'm just kind of wondering, and again, I could be wrong. So for my student at home, forgive me if I am wrong. But if it's at the breaking point, well, I feel like it's at the breaking point. It's not past the breaking point. So if it's at the breaking point, that means the static friction is still acting on this box, right? The box only breaks through the static friction once you break past that breaking point. I'm using the word break a lot. So anyway, if we're at the breaking point as opposed to past the breaking point, static friction is still being applied. And the static friction, therefore, is preventing the box from budging in any particular direction, So that would make the tension 0. All right, because static friction is still acting on the box, which makes the tension 0. Now, one of the reasons why I feel like that could be a misunderstanding on my part is because the teacher's using the word calculate. And calculate seems a very specific word to ask a student to do. The word calculate means that whatever the answer is, it probably requires equations and stuff. But if that's the case, then I don't really have a problem with this. I sort of have a lingering question, though. Is it possible to have kinetic friction on a box that's not moving? I don't know if there is. I don't know if that is possible. So, but I feel like if the teacher had a problem with that, then the teacher would have circled that, So it's very vague with the question marks. So unfortunately, that's as far as I can go with that one. I like this answer to the question. Explain if the answer to part A would increase, decrease, or remain the same if the inclined plane is frictionless. Well, even according to both of our answers, like I said that the tension of the string would be 0. Well, that definitely would change. The tension would definitely increase if there was no friction, because that pulley would be pulling down and then it would hit the tension, right? The pulley would be pulling it down. There would be no static friction to keep the box in place. And then of course there would be tension in string 2. So if it was if my answer is correct, and my answer from the last slide was that there's 0 tension when the box is at its breaking point, then the answer would be certainly that it would increase. The tension in string 2 would increase. Now for my student's answer, I would agree with her that even if her answer on the previous page was correct, then yes, the tension in string 2 would increase, because friction is a part of the static friction max that keeps the block at rest. And also really, kinetic friction, if there was friction is reducing the tension. So I would agree with that. If there's no friction, then the tension in string 2 has to increase to maintain the same force to keep the block at rest. So I don't know why I put a question mark here, because I like that line too, personally. I understand where my student is coming from with that statement. So this is a very vague question mark. Okay, calculate the acceleration of the block. So this is after this string was cut. All right, so that string got cut. Make that a little thinner. That string got cut right there. So now the block's moving, and this is going down, and this is moving. We want to calculate the acceleration. So There was a previous problem where when we calculated the acceleration of a pulley, I just kind of cut to the chase and said A equals the force of this going down all over the sum total of all the masses being pulled. So I'll say that again. Before, in a previous problem, I said A equals this force going down all over the sum total of all the masses. But that only works if there's no friction. When there is friction, you have to do all this other crazy stuff. And it actually looks like my student's doing it very well. So basically, what my student is doing here is this equation is essentially acknowledging the Newton's law that says you have the force, or we could say the net force in a particular direction is equal to the mass times, um, you know, acceleration, right? Force equals mass times acceleration. Well, what is this force? Well, this force here is this actually, right? It's this T1, you know, because this is basically describing this box. This box is going up in accordance with T1, but then we have to subtract away the kinetic friction, which is trying to push it back, right? And then we also have to subtract away this vector component here. Essentially, gravity is acting on this box too and trying to slide the box down. And that's where this vector component, mg sine theta, comes into play, which is written on this free body diagram, which is really, really great. So you have the friction pushing back. The tension too is gone because the string was cut, but you still have the friction pushing back. You have the gravity sort of acting on the box, trying to get the box to slide down the hill, but you also have this tension, bringing it up. So the net force is going to be that tension minus all those countering forces, and that's going to equal mass times acceleration. So I love that. My student should be very proud of herself. First of all, the handwriting is fantastic. And second of all, look, it's not easy. What she's doing is not easy at all. So then there's this one, though. She sets up another equation, which I really appreciate, that basically is alluding to what's happening here, where you have this force going down, mass times gravity, we could say. Mass times gravity. Well, guess what the mass times gravity is? It's 3m times gravity, right? Because the mass is 3m. So it's going to be 3m times gravity. So I really appreciate that my students take into account that, okay, well, whatever this force is, it's definitely going down, but then we have to subtract away this tension. Now that tension is T1, which is the same tension over here. This tension is the same as that tension, so she can absolutely get away with calling it T1. It appears as though what she did then is she used what's a system of equations ultimately. She essentially used elimination. She added the top red equation to the bottom blue equation. She canceled the T1s, which is great. And then what's left on the left side? Well, we have 3mg minus mg cosine theta times mu k minus mg sine theta. I mean, that's all this stuff. That's all the stuff that's on the left, right? Except for the T1. And then when she added the MA plus the 3MA, she got 4MA, which is very, very good. And really at that point, so for my student at home, great job, unbelievable, like really, really good. And I think that the bottom line is you're just done here. You're done here. And that's the only issue. That's the only thing I really have to say about that, because that right there should be the final answer, I think, because what you did is you saw an opportunity to solve for acceleration right here by just dividing both sides of the equation by 4m, which is what you did. And then you have acceleration equals this big mess over 4m. All right. Now, in a way that is related to the equation that I had mentioned earlier in the video, where you have the sort of net force acting on the system all over the the total masses, the sum total of masses in the system. So in a way, it's the same thing. It just turns out that the net force is acting upon the system. You have to take into account, friction and all that stuff, right? So anyway, great job with that. And I guess my teacher is just not, or not my teacher, your teacher is not a fan of you factoring stuff. I mean, I think that's kind of, you know, it's possible that in your math class, so this is directly directed at my student at home. It's possible that, you know, in your math class, you're used to seeing something like this, and maybe it's torture to leave it like that because you've been trained in your math class that, well, maybe I could simplify this more. Maybe I could put the 4m underneath everything. I see opportunities to cancel this m with that m. I see opportunities to cancel that m with that m with that m. So maybe there is an opportunity to cancel stuff. It does look like your teacher was happy with this though, so that is something to think about. If I was to simplify it, because I would understand that the presence of the m's are annoying, right? So let me see. What would I do? I definitely would cancel the m's out. You know what? I think that's okay. I think you can cancel these out. That's not the end of the world. And then you could say, oh, okay, 3g minus g cosine theta times mu k minus g sine theta. To be perfectly honest, I don't see a problem with that. Just put a little 4 underneath it. But I think I would probably leave it there. This sort of factoring out of the g, which is understandable. You see these g's. It's not that it's wrong, but you know, you just don't have to. This is not simplified. Okay, this is factoring in a weird way. Factoring is really useful in math, but in a way, factoring is actually stepping away from simplifying. Whereas, had you distributed the g back into it, that would be simplifying it. And I think what your teacher wants, your physics teacher, wants a fully sort of simplified answer, which means you don't want to leave it in factored form. Doesn't look like it's the end of the world. I guess that's an X. I guess he took off 1 point because he was annoyed by it. Okay. Also, I would say that to, let's see, what did you do? Okay, yeah, we also have an issue here where you decided that this 4 that's in the denominator only needs to get applied to the first term, and that's not true. In reality, that 4 is getting applied to all 3 terms. There's 3 terms. There's this term, is kind of a big term, and then there's this term, and in reality, the 4 is going underneath each one. But we don't really need to do that. If you were to do that, I think you get it. But if you were to do that, it would have a 4 there and a 4 there. But, you know, honestly, that's kind of ugly looking. I would say that that's not necessary. You're better off either with something like this or with something like that. All right, so for my student at home, not the end of the world. You completely crushed the hard part, which is, you know, challenging and lots of room to make a mistake. I would strongly suggest either leaving it here with the m's in there. I don't know how much your physics teacher cares about you factoring out or canceling those m's out, but if you really want to cancel the m's out, because you could, and we could say that that would be an act of simplifying it actually, then this would be the fully simplified answer as far as I could tell. Unless I'm not writing something. I got the mu k, I think I got everything, g sine theta. So anyway, that's what I would say. But anyway, honestly, I know this class has been challenging for my student, but I do believe she absolutely has what it takes to get through this course. And hopefully for some of you guys watching this, probably not the best video to watch. It's not the most educational because I'm just kind of rapping on these problems. But, hopefully you followed some of it. If you have any comments or questions, let me know. If you saw me make any calculations, incorrect calculations, any careless mistakes, please let me know. But other than that, I will see you soon. For my student at home, hopefully this is helpful. That last problem with the tension, thinking that the tension might be 0. Yeah, it's probably not 0. The tension of T2 is probably not 0. But then again, I still wonder what problem your teacher had with your answer. I'm not quite sure. So that's something we can sort of reconnect about at some point in the near future. So, anyway, hopefully this was helpful, and I will talk to you later. Bye.